absolutely drowning in text, don't we? I mean, emails, articles, research papers, legal docs, notes, it's everywhere.
It really is. And pulling useful information together often means you have to look across a whole bunch of those sources at once.
Exactly. But here's the kicker. Our best language models, the really powerful ones, they kind of struggle with that, especially when you try to scale it up. Reasoning across many documents is tough. So today we're doing a deep dive into this really fascinating paper. Researchers at UC San Diego came up with a genuinely novel idea to tackle this exact problem.
Uh-huh.
They call it document super, and it uses the latest structured state space models, specifically Mamba 2.
Right. And our mission today is really to unpack that strategy. We want to dig into how it works technically, understand why it's effective, because some of the findings are quite surprising, actually.
Surprising? Okay, interesting.
Yeah, and see why it's a potentially significant step forward for handling these large dynamic text collections. We'll look at the mechanics, the academic innovation, and, the performance.
Okay, let's set the stage first. Why is this multi-document reasoning thing so hard? I mean, can't you just, I don't know, staple all the documents together and feed them in?
Well, you can, and that's basically the traditional approach, what they call concatenation encoding. You take all your docs, maybe stick the query in there too, and flatten it all into one massive sequence,
Right, one long chunk.
one long chunk. But the fundamental problem, especially for the models most people use, the transformers, lies in their coring design, that attention mechanism.
Ah, attention. We hear a lot about
We
that.
do. And its computational cost, the processing power, and the memory it needs, it scales quadratically with the length of that input sequence.
Quadratic OL2. Right, that sounds computationally expensive when L gets
It
large.
gets very expensive very fast, OL2. So processing even one really long document is tough, let alone trying to concatenate dozens or hundreds. You hit a wall pretty quickly in terms of compute and memory. It just doesn't scale well. Now, you mentioned state space models, SSMs like MABA. They are much better with long sequences. They scale linearly, OIL. Huge improvement there.
Okay, so problem solved with SSMs.
Well, not entirely if you stick with concatenation. Even with an efficient SSM, if you treat the whole collection as one big fixed input block, think about what happens.
Okay.
If you want to ask a new question using the same set of documents, or worse, if just one document in your collection changes, or you want to query a slightly different
You
subset,
have to re-encode the whole thing again.
exactly, you have to reprocess that entire monolithic block, which is super inefficient and just too rigid for how we actually work with information, where things change and we ask different questions.
Ouch. Yeah, that sounds clunky. Okay, so even linear scaling for length doesn't fix the process inefficiency, and that's where this document souping comes in.
Precisely. The UC San Diego team got inspired by something called model souping. That's a technique where people average the parameters, the weights of different trained models to sometimes get better results.
Okay, averaging models.
So they asked, what if we could soup something else? Not the model parameters, but the hidden states the body generates while processing individual documents separately.
Whoa, okay, souping the states, not the model itself. How does that actually work, like mechanically?
It's actually quite elegant, and it hinges on a key property of SSMs. So instead of mushing all the documents together before encoding,
Right.
you encode each document independently. Doc 1 goes through a shared SSM encoder, you get its hidden state. Doc 2, same encoder, different hidden state, and so on for all the documents you care about. And the really crucial bit specific to SSMs is how they work internally. They're designed to compress these variable length inputs, long doc, short doc, doesn't matter, into fixed size hidden state vectors at each layer.
Ah, fixed size. So every document, regardless of its actual length, gets summarized into a state vector of the same dimension.
Exactly. At a given layer, the state vector for document 1 has the same size as the state vector for document 10. And that's what makes them combinable. So you take these individual fixed size document states from the same layer across all your documents. And then you pool them, merge them together using really simple math, like
Um,
element-wise averaging or summing them up or taking the maximum value for each position in the vector. Simple commutative operations.
Okay, so you're essentially creating a single summary state by mixing the individual summaries, like making a soup from different ingredient flavors, but with these hidden state vectors.
That's a great analogy. You get this single soup state for that layer, representing the combined context. And that soup state, along with your query, is what you feed into the model's decoder to get your answer or perform your task.
Okay, I can immediately see the appeal there. It sounds way more flexible. You encode each document once, maybe offline, store that state,
Right? Cache it?
cache it, and then when a query comes in or you want to focus on a different set of docs, you just grab the relevant cache states and
Yeah,
soup them up dynamically. No need to re-encode this giant blob every single time.
exactly. That dynamic mixing and matching, that reuse, It offers potentially huge efficiency gains for real-world systems dealing with changing information.
It sounds almost too good to be true, though. Does combining these separate summaries actually work? Does it preserve enough information? Which brings us to this idea you mentioned, soupability.
Right, soupability, that's the core property they investigated. It's not just about can you mathematically combine the states, obviously you could average vectors. It's about whether that combination is effective.
Effective for the actual task, like reasoning.
Precisely. Can you combine these independently generated hidden states using simple pooling, like averaging, and still retain the rich information, the relationships, needed for complex downstream tasks that require understanding connections across those documents?
And is it surprising that it does work? Because my gut feeling would be that processing everything together from the start, letting the model see all the connections directly, should be better than mixing summaries later.
And that's where the really interesting academic finding comes in. It is quite surprising that simple aggregation works so well. And importantly, they found that if you just take a pre-trained Mama 2 model off the shelf and try to soup its states, it doesn't work very well.
Ah, okay. So it's not inherent to the pre-trained model.
No, the pre-trained encoder doesn't automatically produce states that are ideally suited for this kind of simple merging, and the pre-trained decoder has no idea how to interpret this soup. The magic, the real innovation, happens with fine-tuning.
Fine-tuning. So you have to train the model specifically for this souping task.
Yes, they showed two key things. First, even with just decoder-only fine-tuning, where you freeze the encoder that makes the states and only train the decoder to understand the soup performance, improves a lot.
Mm.
Which tells you that those initial independently generated states from the pre-trained encoder already contained a surprising amount of the necessary information. The decoder could learn to piece it together from the average state.
Okay, so the info is kind of latently there.
Kind of, but the best results, and this is really a core academic contribution of the paper, came from full encoder-decoder fine-tuning, training the whole system end-to-end with this souping objective.
What happens then?
Then the encoder actually learns to produce representations, hidden states, that are intrinsically more mergeable. It adapts to generate states that are designed from the ground up to be effectively combined through simple averaging or summing. It's not just the decoder interpreting better, the encoder actively learns to create soupable states.
Wow. Okay, that is cool. The model learns how to make its own internal representations combinable. So getting into the weeds a bit, you said they tried different pooling methods, averaging, summing, mass pooling. What was the best recipe for the soup?
Yeah, they tested those and also looked at using normalization, like L2 norm, before-after pooling to keep the Victor magnitudes in check.
And the winner was?
Surprisingly, the most robust and consistently effective method across different tasks and different numbers of documents was just simple element-wise averaging without any normalization.
Just average the vector. That feels almost too simple for these complex models. Why would plain averaging work best?
Well, the thinking is that averaging strikes a good balance. It pulls in information from all the documents. But crucially, by doing it without normalization, it seems to implicitly maintain a more stable scale and direction of the resulting averaged vector.
Okay, scale and direction.
Right. That directional information in the high-dimensional space seems really important for the model. Summing, on the other hand, especially without normalization, can cause the vector magnitudes to just grow and grow as you add more documents, potentially overwhelming the signal.
Ah, unbounded growth. Bad.
Bad. And while normalization can console that magnitude growth, it seems that applying it actually sometimes hurt performance compared to simple averaging. It suggests that maybe the relative magnitudes of the original document states contain useful information that normalization washes away, but simple averaging preserves.
Fascinating. So sometimes the simplest approach really is the most robust. Okay, besides the mixing method, what about generalization? How well does a souped model handle seeing a different number of documents at test time than it saw during training? That seems crucial for real-world use.
Yeah, that's a really important question they looked into. And the results were interesting. Generally, performance is best when the test soup size matches the training soup size. Makes sense, right? It's optimized for that.
Sure.
But here's the key insight for generalization. Models that were trained with larger soup sizes, say, trained by averaging states from 8 documents, actually generalize better when tested on even larger soup sizes, like 16 documents, compared to models trained on smaller soup sizes, like just 2.
So training with more documents, even if it's the same total amount of text just broken up more, helps it learn a more robust way to combine things.
Exactly. It seems that training on more fragmented input forces the encoder to learn representations that are inherently more compositional, and the decoder becomes better at handling variations in the number of sources it's getting information from.
That makes it more tolerant to changes in how many docs you feed it later on.
Precisely, which is super valuable for flexibility. They also noted, perhaps unsurprisingly, that larger models, they used an 8 billion parameter Mamba 2 versus a 2.7 billion one, were generally more robust and generalized better across different soup sizes.
Okay, so the technical approach is sound. It has these interesting properties like soupability learned through fine-tuning, good generalization. But the proof is in the pudding, right? Does it actually perform well on hard tasks?
Yes, and that's crucial. The paper shows strong results. On multi-hop question answering, like the HotpotQA benchmark, which absolutely requires connecting facts across different documents.
Right, the whole point is reasoning across docs.
Exactly. On those tasks, the souping method performed nearly as well as, and sometimes even better than, the traditional concatenation approach, which is a big deal. It shows that this simple pooled state does capture enough of the cross-document relationships to do complex reasoning.
That's impressive. What about really long documents?
Good question. On long document QA benchmarks like Quality, they found that models trained using souping on shorter texts actually generalize quite well to much longer texts at inference time.
Unlike concatenation, which tends to struggle beyond its training length.
Right. Concatenation often sees performance drop off sharply if the test input is much longer than what it was trained on. But souping, because each document chunk, no matter how long, gets compressed to that fixed size state by the SSM, seems to provide a more length invariant way to combine context. It handles length variations better.
And other tasks.
It also performed well on sparse retrieval tasks, showing it can preserve the fine-grained details needed to pinpoint specific facts within a large set of documents.
Okay, so this isn't just some theoretical curiosity. It delivers competitive, sometimes better, performance on challenging benchmarks. Plus, it seems to handle length better.
And then there's the efficiency payoff we touched on earlier, which is huge in practice. Because you encode documents independently,
You can do it in parallel.
massively parallel. And once you have those hidden states computed,
You cache them and reuse them.
exactly, cache and reuse, that's the game changer. No need to re-encode the whole corpus for every new query or every small change. Just grab the cache states you need and soup them. It cuts down massively on redundant computation.
In memory.
For inference, you're just dealing with that relatively small, fixed-size pooled state, and the query very memory efficient compared to holding a giant concatenated sequence. Now, for training with lots of documents, they did mention using standard techniques like activation checkpointing.
Ah, yeah. Trading compute for memory during training.
Right, you recompute some things during the backward pass instead of storing everything. It's a common way to make training on very large inputs or with many documents feasible on current hardware.
So it really enables this workflow, pre-process a ton of info once, efficiently store these compact summaries, and then query flexibly across any subset you need.
It certainly points in that direction. And, giving credit where it's due, this builds on foundational work. Obviously, the SSMs themselves, Mamba 2 from Gu and Dao, are critical.
Sure, the underlying engine.
And the concept was inspired by that parameter-based model souping work, like from Wartzman and others. But applying this souping idea specifically to document states within SSMs for modular multi-document reasoning, that's the novel contribution here.
Did they mention any limitations, things they didn't get to test?
Yeah, they were upfront about a couple of things. Due to compute resources, they couldn't really push the envelope on the number of documents being souped, like testing with 128 or even more documents simultaneously. So how well it scales to extremely high levels of fragmentation is still an open question for future work.
Okay, practical limits.
And they also didn't provide, a detailed, large-scale benchmark comparing the end-to-end training and inference speed and memory usage under realistic deployment scenarios versus other methods. That kind of practical system-level benchmarking is complex and left for future investigation.
Got it. So let's wrap up this deep dive. We've unpacked document souping, this really neat modular way to use state space models like Mamba 2 for multi-document reasoning.
Uh-huh.
The key idea, encode docs separately with a shared SSM, get these fixed size hidden states, and then just pool them together. Simple averaging works best, surprisingly.
And critically, this superability isn't automatic. It's something the model learns effectively through fine-tuning, especially full encoder-decoder fine-tuning.
Right, and this approach seems robust to varying numbers of documents, generalizes well to long texts, performs strongly on tough QA tasks, and offers potentially huge efficiency wins through parallelism and caching.
Yeah, it really provides a strong foundation, I think, for building more flexible, scalable, and efficient AI systems that can actually grapple with the enormous dynamic information landscapes we have today. It's a clever way to handle complexity at the architectural level.
So here's something to think about. Consider the sheer volume of text in your world. Maybe research papers, legal cases, internal company reports, news archives. If models can efficiently soup insights from hundreds, maybe thousands of these sources without that massive recomputation bottleneck, what new kinds of deep analysis or discovery could that unlock for you? What problems in your field might suddenly become more tractable? Definitely something to mull over. Keep exploring.